Hello Mario! In this video I'm going to be looking at how my old friend Pythagoras can be dragged out of the surveyor's toolbag to perform any number of things during the day. So let's have a look at the first instance where we might be able to use Pythagoras. So we'll just turn that layer off there and turn this one on here, and we'll drag out my trusty HP 15C calculator to perform the calculations that we need. So first of all, we need to know that Pythagoras applies to the right angle triangle. The right angle triangle contains a right angle 90 degrees, and there are various names and things that we attribute to the right angle triangle. In the first instance, what I like to do is to label the triangle with A, B, C. That's big A, big B and big C, and big C being the right angle. And then the angle opposite each one is then given a lowercase, so A opposite A, B opposite B, and C opposite C. C also is called the hypotenuse. It's always the longest side of the triangle, and it's always opposite the largest angle. This is something that is true for all triangles, in that the largest side is always opposite the largest angle, the smallest side opposite the smallest angle, and, well, the middle side is opposite the middle size angle. Just, I guess, like the three bears in a way. So, and the theorem of Pythagoras, well, what it says is that the square on the hypotenuse is equal to the sum of the squares on the other two sides. Or, you can just write it quite clearly, A squared plus B squared equals C squared. So in the example that we've got here, we have A as 184.63 and B as 71.26. So A squared, 184.63 squared, and B squared, 71.26 squared, and that's equal to C squared. But hang on, we don't want to know what C squared is, we want to know what C is. So we take the square root of it. So C equals the square root of 184.63 squared plus 71.26 squared. So let's go to the old 15C and let's see what that has to say about that. So we put in 184.63 and we square that just here, square that, and then we put in 71.26, square that again, x squared, and then we just add those together and take the square root, and there we go, we get 197.9046. that's to 4 decimal places, but our information has been given to us to 2 decimal places, so we show our answer to 2 decimal places. That's how accurately we measured it to start with. That's how accurately we will show our answer, and we get 197.90. Now this is meters, we're surveyors, we work in meters. I don't think really necessary to show the M, little m there, to show that it's meters, but you know, if you want to, that's up to you. So let's have a look at another one here where we've got another right angle triangle. I've labelled it ABC, as I said, little a, ABC, and in this case here I've forgotten to sort of let you know that the 97.46 is the hypotenuse, but you know, I think you can pick that up. We're hoping you are, after that fine explanation I've just given you. Now, okay, so let's write out our Pythagoras. A squared plus B squared equals C squared, but we want to find B squared. Well, we just got to rearrange the formula a little bit, get all the things that we know on one side and the things we don't know on the other side. So we could just well, I've put it around the other way. So I've got C squared, I've taken A squared off both sides. What you do to one side you must do to the other. So C squared minus A squared equals B squared. Pretty simple. So that means B because we don't want b squared, we want b, is the square root of 97.46 minus 71.64 squared. 97.46 squared. Alright, so back to the old 15c, and here we go. 97.46, and let's square that. And then, now this is a reverse Polish notation calculator. It might be a bit different to what you use, but you'll get the idea, and it's downloadable from HP in this current form. It's a it's a calculator that a lot of surveyors, older surveyors, will have used. I used this particularly when these calculators first came out quite a few years ago. Alright, so there's 71.64 squared, and we just subtract that. Alright, and that is actually b squared, and then we take the square root of that, and we get 67.0769, which we round to 66.08. The information we were given had 2 decimal places. We'll stay with that and give the answer in a similar way. Alright, now moving on. So we just, what we do here with this smooth draw 3, yes, it's the same one that they use for the Khan Academy. Here we go again, and this is our next problem. Arnold measured 748.64 from station A to B, and then he measured 527.43 due east to station C, and we know north is up the page, a usual convention with surveys, but I've got a little arrow here showing that. How far does he need to measure due south to get back to station A? So we're mentioning directions here, so the answer should have a direction. We're dealing with sort of vectors, so just remember the answer should have a vector. Now let's drag out our Pythagoras, and here's a squared plus b squared equals c squared, and I've sort of left out a few steps now that you're used to this, and I've got b is equal to the square root of c squared minus a squared. So we've jumped a few steps there. You could put the other ones in if you want to go back in the video, but it's pretty, you should be pretty conversant with it now. So here we go. B equals the square root of 748.64 squared minus 527.43 squared. So here we go into the 15C. 748.64 x squared. Oh, that's a pretty large number. And then we go 527.43, and once again that's x squared, and we take it away from the previous one, and well, take the square root of it, and we get 531.2998, 531.3 to 2 decimal places, because well, we started with 2, we'll give it that accurate, and we've got a little direction there, due south. So there you go, a distance and a direction. Who would have thought? Okay, now we're going to move on to something else that goes a bit beyond the realms of Pythagoras, but nonetheless is related, and this time we're going to be working with angles and the trig ratios. I've done other videos on the trig ratios, so you could look through my channel if you wanted a bit of background on those, but I'm just going to assume that you know a little bit about them. So Julian wants to know the difference in height between point A and point B. He stands at point A and measures an angle of 37 degrees 12 minutes 05 seconds. Again, I've done videos on this format, 20 degrees, minutes and seconds, on my YouTube channel, so have a look there, or you could get back to me and I could point you in the right direction, or I may need to make another video if I think it's gonna help. And with us, and to B, so he's measured that angle to B with a slope distance of 746.21. What is the difference in height? Now this is just using your trig ratios, sine, cos and tan, and there's a number of different ways of doing this and working out which one to use, but I use the what we call the SOHCAHTOA method, and that's where we write down the SOHCAHTOA and each one of those stands for a different aspect of a triangle. So sine opposite over hypotenuse, cosine adjacent over hypotenuse, and the tan opposite over adjacent. So here we have the hypotenuse. Here's the angle that we've identified. We know that. So the side opposite the angle is actually x, the one we find, and the side adjacent to it is here. We don't know that, and we know the hypotenuse. So what we do is we've got an angle, so immediately we can tick S, because we can find the sine, cosine and tan of those angles. We want to find the opposite, so we put a question mark over the opposite, and we know the hypotenuse and we don't know the adjacent. So 2 ticks and a question mark, that's the one. That's 2 ticks and the question mark, that's the one we go for. Sine, so the sine of angle B equals the opposite over the hypotenuse, and so that's sine 37 degrees 12 minutes 05 equals x, which was the opposite, over the hypotenuse 746.21, and then we can multiply both sides by 746.21, and that'll give us x equals sine 37 degrees 12 minutes 05 times 746.21. So now off to our HP 15C for a bit of a look at how we're going to deal with that. So first thing we've got to do is put in our bearing, 37.1205, and that's in the degrees, minutes and seconds formula, and then we've got to convert that to decimal degrees or to hours. Decimal hours is the same thing, like so. So we do that, and then we take the sine of that, and then we go 746.21 times, and we get 451.1723. We put our answer, x equals 451.17. Once again, started with 2 decimal places, will end with 2 decimal places. It's an indication of the accuracy that we're working to. It would be most unrealistic to give the answer to any more than 2 decimal places, given that we haven't measured the original measurements to any better than that. Alright, so let's move on with more of the stuff that is attributed to Pythagoras in some ways and related in others. Calculate the horizontal distance between A and B to 2 decimal places. We'll ask for 2 decimal places this time. So yeah, so what we've got here is an angle, 11 degrees 27, and we've got a slope distance of 187.25. Let's crack out the SOHCAHTOA. Again, tick, 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 we've got an angle. We want to find the opposite, so we can put the question mark over the... what one do we want to find? We want to find the adjacent, and I've actually got the x in the wrong place, but hey, I make mistakes just like anyone else, and I can possibly just fix that straight away by just getting in here with my little pen and just going edit, cut, and let's just paste that somewhere else. There it is there, and I'll just drag it over there so x is just there where we want to find it. Okay, so that's that one sorted. Not too much problem there. So yes, we want to find x, the adjacent. So cosine 11 degrees 27 equals x, the adjacent, over the hypotenuse, which was 187.25. So x equals cos 11 degrees 27 minutes times 187.25. Once again, we bust out the 15C, and here we go, 11.27. Now we've got to convert that to degrees and decimals. Use the 2 hours one. Take the cosine of that, and then we multiply that by, can push enter, 187.25 times, and we get 183.5234. Once again, 2 decimal places, 183.52. You'll note that when you're doing slope distances and reductions and things like that, you would expect it to be the cosine be very close to 1, because you're just reducing the smaller the slope distance to the slightly smaller horizontal distance, or usually. And yeah, an angle of 11 degrees is sort of relatively steep in some terms, but yeah, just a little bit of surveying context there. Alright, so let's move on now. We've got a couple more little problems to look at, and on a similar vein. So here we go. Calculate the marked angle theta in the triangle to the nearest second. So here I've got the triangle all labelled up as best I can, got the hypotenuse in this time, busted out my SOHCAHTOA, but I've forgotten to put my traditional little red line along the one I'm going to choose, so I might try and just sort that out for an hour. So SOHCAHTOA. So in this case we want to find an angle, so we put the question mark over the S, the C and the T. So what do we need? We need 2 ticks and a question mark. We know the opposite, we know the hypotenuse, so click through the opposites, we know those and we know the hypotenuse, but it looks like the one we're going to have to use here is the sine ratio. Okay, so I'm just going to try and put my little red sign around there. I'm sort of pushed a few wrong things, but there we go. So it's that one there. That's the one we're going to use. All good. Okay, so now we can say sine of theta equals the opposite over the hypotenuse, and that's 5.2 over 56.1. Just a little note there that they're just to 1 decimal place. However, the question has asked that it be calculated to the nearest second. So theta equals sine to the -1, which is the inverse of the sine of 5.2 over 56.1. So how do we do that on our calculator? Well, what we do is we put in our 5.2 and we push enter, and 56.1 divide. Now this is, the calculator is holding on to a lot more decimals than that. If I was to fix 8, it would show it to 8 decimal places, but I like to have it fixed at 4, because that gives us to the nearest second when we do. So now let's remember that that's the sine to the that's there, and then that's our calculated 5.2 by 56.1, and so then we go sine to the -1, which is here, and that's giving us our answer in degrees and decimals, but we want it in degrees, minutes and seconds. After all, that was the way that that's the way that we've been dealing with all the other ones, and they want it to the nearest second. So we just push here to hours, minutes and seconds. 5 degrees, 19 minutes and 7 seconds. It's important that the 0 be in there, that you show it in that format of degrees, minutes, mm and ss. So you always have your leading and trailing zeros in there. It's because it avoids confusion, makes it absolutely abundantly clear what's going on. Alright, so we've got a couple more to go now, just to show our newfound skills. Alright, calculate theta in the triangle below to the nearest second. Once again, we've just got them to the nearest meter here. All labelled up A, B, C. Here's our angle that we're wanting. We've got our opposite labelled and our adjacent. So the opposite and the adjacent and the hypotenuse there. So getting out our SOHCAHTOA, question mark over the angles. We know the opposite, tick the opposites. We know the adjacent, tick the adjacents, and that tells us that we're going to be using the tan ratio. So tan theta equals opposite over adjacent. Tan theta equals 70 over 100. Now I can work that out in my head, that's 0.7, but I'm going to do it in the calculator, because in case you encounter some trickier numbers that you can't do it in your head. So I'm just letting you know that I can do it in my head, just so you don't think I'm a bit lame, just putting it on the calculator, but I am just going to show how that does. So I know the answer is 0.7, but I'm just going to prove it to you. So here we go. 70 enter, 100 divide 0.7 as predicted, and then we go shift tan to the -1, and that's in, remember that's in degrees and decimals, so we've got to convert that to like that, and that gives us 34 degrees 59 31. Woohoo! We've got that one to the nearest second, and we've nailed it. Okay, now just one more to go. This one's getting quite contextual. Wilhelmine, unusual name, but a friend of mine, Wilhelmine, is 67.42 from the base of a building. She measures a 27 degrees 52 minute 38 second angle to the top of that said building. What is the slope distance from Wilhelmine to the top of the building? Yeah, good question. Okay, so I've got the diagram all here, the right angle here. I've got me A, B and C as always, and my hypotenuse in here. Here's my angle, here's my opposite, here's my adjacent, and I've got some little windows in my building here, just two, so we know it's a building. So we tick off the angles. Oh, I've got a little bit remiss here in that I haven't crossed out my I's, but hopefully by now you get the idea. And so we know the adjacent here at 67.42, labeled it. I've also labeled it as A as well, but it is the adjacent. Oh, it's actually B, side B, but adjacent and opposite. So it can be a bit confusing, but you just got to go with it. So cos of A equals the adjacent over the hypotenuse. So we go cos 27 degrees 52 minutes 38 equals the adjacent 67.42 over x, which is the hypotenuse. Now, it gets a bit tricky here. So we multiply, just multiply both sides by, we multiply both sides by x, which will give us x cos 27 52 38 equals 67.42, and therefore x equals 67.42 dividing both sides by cos 27 degrees 52 38. So let's work that one. Let's work that baby out. All right, 67.42, and we just push that enter. That just puts it up into the y register, and then we go 27.5238. Convert that to degrees and decimals, or to hours, and then we take the cosine of that and we divide, and we get 76.2711, which we show our answer to the nearest, or to two decimal places, 76.27. So there you are, some little instances of Pythagoras and trig ratios and things like that put into the context of the surveying, context of a surveying worksite. Pythagoras, a little tool that you can drag out of your toolbox on many an occasion to solve a problem relatively easily. Cheers!